Zombie apocalypse.
Good day, everyone. So I'm here now to present one of the most or highly talked topic regarding to the world of physics, that is the principle of relativistic mass and energy. So I'm here to give you some information about this one, and actually this will serve as my report to my dearest professor in Advanced Physics 2, or also known as Modern Physics, under the supervision of Dr. Dante Garrido of Masters of Engineering Program, no, under the School of University of the East Manila Graduate Program. Okay? So, be ready to be neurorized. Okay, so let's talk about first, ano ba yung pinaka konsepto ng relativistic mass and energy by looking at the physics of mass and energy as an equivalence. So let's take a closer look how are they are being correlated. But of course, let's talk about this kind of situation whereas a lot of philosophical attention has been paid to how the meaning of statements concerning lengths and time changes in the context of special relativity. Here comes the problem. According to Newton, that let's say an apple falling from the tree towards the ground, the question would be, of course, there should be an observer within the area, or maybe nearest to the falling apple. So the question would be, is the observer correct saying that the speed or the rate of fall of that particular apple is the true velocity of that particular material or particular object, which is the apple? The question would be, is the ground itself is really not moving? Because when we talk about velocity, it seems to be that as we perceive the definition of the speed, it is actually the observation from the observer based on what he can see on that object. However, what if that observer is on a moving vehicle and then there's something like, you know, an apple falling from the tree, and then can he correctly say that the speed that he is seeing is the true speed of the apple? So that would be the concept behind. So therefore, this is now the evolution of the relativistic mass and energy, and some, of course, some concepts like relativistic mass, relativistic time, or what we call time dilation. Also with respect to simultaneity and relativistic length, of course, as we call it, the length of contraction, and relativistic velocity. Okay, so those are the the talk abouts regarding to this kind of topic. Now, in relativity of mass and energy, as Heck says, he emphasized that Einstein never wrote down his famous result using the symbols like E. No, this is very popular, E and M, whereas M is the mass of the particular energy or particle, and E is what you call, it can be the rest energy or the total energy. But let's try to talk about later on how do we qualify when it is total and when it is under rest energy. Although part of the reason is merely that Einstein used different letters for energy, mass, and the speed of light in his early papers discussing those equivalents in mass of energy. No? In 1905 and 1906, deeper reasons related to how we should understand the result quickly emerge. So nagkakaroon po dito ng parang konting debate kung ano po ba talaga ang existence ng velocity, in relation to an object. Of course, it has mass, it has, of course, the length itself, of course, the dimension is present. So there's something like a proposition about what is true and what is false, okay, or what is more realistic. Now, in his review of the article, he says that from 1907, of course 1907, Einstein shows that a body of mass, let's say in terms of mu, that has absorbed an amount of energy is of naught, as I mentioned in its rest frame, executes motion. So meaning the object under rest condition. So therefore, an inertial frame relative to which it moves with some velocity and its mass big M was given by the expression, as we know it already, no? That M is equal to the mu plus E sub naught all over C squared, whereas C represents the speed of light. In a footnote, Einstein explains that the convention, which he had already adopted in an earlier paper, Einstein, and according to it, no, under page 250, of using the substitute O or subnat, as we call it, to indicate that the quantity in question refers to a reference system, or actually the base reference, or the so-called the origin of all readings. So he relates that it is at rest, so that we can have a better idea of what is the true value of any moving object, that it can be observed by an observer in a rest condition, okay, or a stationary condition, according to the page 286 of his report. Now, after 1907, Einstein's notation crystallizes, so that by 1921, in his Princeton lectures, he gives his famous result by writing that E sub naught is equal to mc squared. So he is referring actually, that particular equation is really understanding the condition of an at-rest condition. But the question would be, is that true that all objects are always being measured by at rest, or are all objects, no, in relation to the speed of light, are always at rest? Of course, there is a condition where the object will move, and of course, as the object moves, it is dynamic and it exerts energy. Of course, there should be a work done to be happened. However, it is important, before going much further, to note that Einstein, the equation of E sub naught is equal to mc squared. The symbol m is the mass of an object as measured in the inertial frame, or in the frame where it is being considered, in which that the object is at rest. So meaning we are going to understand that the base reference of any idea is taken from at rest before it moves. Of course, indeed, I do believe that whenever we try to measure an object, we it seems that we think that we, as the observer, are at rest. Although, we have this kind of situation, let's say you're riding in a jeepney, and then you're sitting there, and then it seems that there is a fly following you. So, what would be the what will be the true velocity of that particular fly following you, whereas you are inside a jeepney that is moving? So will it be your observation, or will it be the true reference, where we are going to see where the value of the true velocity of that particular fly will rely? So that would be the question, as for this statement here goes. Okay, let's talk about the symbol and meaning. Okay, notice that E sub naught is equal to mc squared. It's very popular. That E is a total energy. Now, when we talk about total energy, meaning you're talking about a dynamic response of that particular particle to move. So therefore, what would be the resemblance of that energy as we go along from rest to a moving object? Okay? So E sub naught represents the rest energy, and M as the mass at rest of a physical system. Now, to better understand what is ongoing to that particular equation, let's take a look on this particular idealized physical interaction. No, this is suggesting that a certain conservation principles are true, such as the principle of conservation of energy and the principle of conservation of momentum. Of course, as we go along with dynamics principle, then any particle, any object may suffer motion, and of course, when there is motion, there can be a possible energy of generation. Then energy can be under what form? Of course, it can be potential, it can be dynamic, kinetic, and whatsoever, as long as it is being conserved. The two principles of the core of special relativity are true. The principle of relativity and the light principle. Okay? And lastly, a body treated as an unanalyzed whole absorbs or emits an amount of energy E sub naught or at rest as measured in its rest frame. So all in all, the base reference would be always the stationary position. Then, its mass at rest increases as decreases by an amount of the ratio of the rest energy with respect to the square of the speed of light. So the final statement is now suggesting that my comment earlier, that of course, as you see, let's say you're in a jeepney ride, and then and you're seeing a fly following you, it doesn't mean the actual. It may look like the fly is not flying, but actually he's just only carrying your same value of velocity. So therefore, how can an observer say, no, if that is an at rest, so what would be the true value? And how about the length? Can you see that the length of the wing of the fly is the same as if the fly is at rest? So that's another question. That's why relativistic condition, like in the mass, like in the length, and like in the velocity as well as for the time, goes with a principle of computation, because those scientists like Einstein, Heck, and so many scientists already try to decipher this very uh, lengthy and ever lasting search for truth. Seems that they are now trying to dedicate that the concept they are trying to offer is true. Now, let us now examine that the light emission from the perspective of the inertial frame K. So this paragraph will only say that they say how does the light supposed to travel, no, in a shorter sense, with a particular amount of velocity, of course, observing energy. Okay. So therefore, by derivation, by let's say a light striking to a particular direction, as the suggestion of the condition, then we can conclude that the equation that we can generate from this very meaningful idea is E over 2C times cosine of theta, referring to a directional property. It may be inclined. Is equal to, let's say, if you're talking about horizontal position, so one plane condition. So therefore, cosine of 0 is 1. Then E over 2C times V over C. Now, notice that that is the projection, or the path of projection. However, if the light is to be perceived, of course, it will travel to from point A to point B and then go back to A. So therefore, times 2 of which will happen. So therefore, it will happen like in the total momentum of the emitted photons. So we will have the E over C times V over C. So the 1/2 is being cancelled because it returns back relative to K. So therefore, by this principle of conservation of momentum must be equal to the amount of momentum lost by B. Of course, there is what we call the potential uh, loss due to travel. Now, since the velocity b does not change, and if we assume that the classical expression for the moment of b we have, then the work done, no, mv, mass times velocity, equals e, or the energy over the speed of light raised to 2 times the velocity. Then we can conclude, no, by simply arranging, so dn e is equal to mc squared. So therefore, this equation will now try to understand that the energy, relativistic energy, in relation of the mass is equal to E is equal to mass times square of the speed of light. Okay, now I want you to focus on what if the object is now moving. So it is now being considered not that it is not on the position of at rest. So therefore, we need to address the gap between E sub naught and mc squared, because this is actually true if at rest, right? Now, what if moving? So therefore, it may move the same equation, but we have to introduce a factor that might influence the condition, and that is the resolution of Lorentz. Okay, the factor where the time dilation, simultaneity, length of contraction, relativistic mass, and relativistic velocity are being catered. But this, the factor as a function of velocity, now is being considered for the work done to happen. Okay, so then let's take a look on a mathematical expression. It says to be that the total energy is the sum of kinetic energy and rest energy. That's true. So therefore, if we assume that the total energy E is the sum of K, also known as the relativistic kinetic energy, assuming that there is what you call relativistic point of view of velocity and energy, plus the rest energy. So meaning E is equal to K plus E sub naught. Okay? That is the more generic sense. So therefore, using the derived condition of uh, gamma as a function of B, or the Lorentz factor that is already being reported by my classmate, and also through the work of Einstein that is being extended by Lorentz. So therefore, the condition for that is equal to 1 over, okay, let me write as a function of the velocity by derivation of Lorentz, 1 over the square root of 1 minus u over c, speed of the object over the speed of light, raised to 2. So as we supply that, this will be the turnout of the equation. Okay? Now, let's take a relation now. So what would be the next relation that we need to understand? Okay? The work done itself. How do we relate that? Now, to derive the relativistic form of work kinetic energy theorem, imagine a particle moving in one dimension along the x-axis, and of course, to the x direction causes the momentum. Of course, there should be at least two material or two objects to collide, or to experience energy of the particle to change according to equation 39.20, which is this one. The relation of the force as a vector is equal to the differential relativistic linear momentum with respect to time. So that is the work done actually. So therefore, finally, we can arrive to the work equal to the integral from x sub 1 up to x sub 2 of force times of force with respect to the function of the distance traveled. So also that f is treated as dp over dt, or what you call the differential linear momentum, relativistic linear momentum with respect to time, and of course with the strip of distance traveled, or dx. Then we finally realize that as we try to apply those equation and then try to rearrange, and then we will understand this equation will exist. Note that as we supply this meaningful equation, okay, provided by already by this. So therefore, you can have this set of equation, okay? And then substituting, you will find out that as we use the main equation of the work done, and then finally we will try to understand this will be your final integrable equation. So, but where we use the limit 0 and u in the integral because the integration variable has been changed. So, nagkakaroon po tayo ng finiteness of condition. Now, evaluating, we will have this, of course, by integral calculus, we will get this. But we need to recall from this particular chapter 7 where it is being discussed by the work done by a force. Chapter 7 refers to the book of survey as one of our reference. So the work done by a force acting on the system consists of a single particle equals to the change of kinetic energy. So the final minus initial. Wherein, if we assume that if the object is at rest, so we understand, okay, the kinetic energy at relativistic condition is held to be zero. Without energy, without motion. So therefore, the work done is simply equal to the relativistic energy, okay? Or rather, relativistic kinetic energy. Therefore, as we apply that, then K, W is equal to K, replacing that. So therefore, and diba, this is K is equal to W now. So therefore, this one. And then, don't forget that 1 over this equation is also the Lorentz factor for velocity, as a function of velocity, relativistic velocity. So therefore, we will have this meaningful equation and then factoring what is common, mc squared. And finally, we realize that k, okay, is equal to gamma as a function of velocity minus 1 quantity of mc squared. Also, we can safely say here that k is also related to gamma as a function of velocity minus 1, okay, times the rest energy. Don't forget that the rest energy is equal to mc squared. So that's now the relation. That is the claim. of the scientist known to be Einstein, defining the relativistic condition. And this is one of his work. And also as a continuation from the work of Lorentz. So these equations is most likely being used to activate and to view the what we call the relativistic condition, where it is actually the Einstein's equation and the iconic equation, as we call it, because most of us already know that E is equal to mc squared by, as a book is really reiterating it so many times, especially in physics. So this is what I'm saying you earlier, no? That the gamma was function of V is so-called the Lorentz factor. Factor with respect to relativistic velocity, okay? Relativistic time dilation, it's a function of mass for the mass, and function of time for time dilation or simultaneity, and for the function of length for length of contraction. Okay? So in the mid 20th century, some physicists such as Richard Feynman, no, is one actually of the scientists who continue the work of Einstein and try to depict that the mass, okay, at moving condition, at motion, is equal to the mass at rest multiplied by the Lorentz factor. So this is what we call the mass relativistic condition or relativistic mass. Now, using these notational conventions, the iconic E is equal to mc squared is the equation of the total energy of a body function of its relativistic mass. And then that comes with the title of the principle of the mass and energy, no? As our title suggests. But of course, we cannot avoid that there can be some philosophical point of view. So what are those possible philosophical interpretation of this very meaningful equation? E sub naught is equal to mc squared. There are three main philosophical questions that might be concerning the interpretation of E sub naught is equal to mc squared that have occupied the philosophers and the physicists. First, are mass and energy the same property of physical systems, and is that what is meant by asserting that they are equivalent? So the number one says that mass and energy are really of the same property. You are trying to compare an apple with an orange, or is it really an apple with an apple? Okay, number two. Is mass converted into an energy in some physical interactions? And if so, what is the relevant sense of conversion? Of course, energy has so many forms, but the question would be if mass as a converted or mass converting that particular energy into some physical interaction. So where that particular mass or energy as a loss to the mass, no, takes form. So that's another question. And number three, one of the most philosophical one, does E sub naught E is equal to mc squared really have an ontological consequence? And if so, what are they? They have to address and specify this question. Okay, the only combination of the answers, question 1 and 2, that is inconsistent is to say that mass and energy are the same property, meaning they are not the same apple, no, in the other sense. One is an apple, one is an orange. But how can an apple be compared with an orange? So, but that the conversion of mass into energy or vice versa is a genuine physical process. So there is actually a true conversion of that particular energy. And all of the other three combinations of the answers to question 1 and 2 are viable options and have been held at one time or another by physicists or philosophers as indicated by examples given by this table 2. Let's say, different properties like conversion, no? Rindler, conversion is possible, but no conversion said by Toretti, Eddington, Body, and Spurgeon are related to same property and different properties. So there's actually an argument regarding this one. Now, what would be the interpretation of E sub naught equal to mc squared and its hypothesis concerning the nature of matter? This very, controversial. So to explain how some interpretation of mass energy equivalence rests on assumptions concerning the nature of matter, we need to first recognize, as several authors have pointed out, for example, Brindler, 1977, Stachel and Toretti, 1982, and Mermin and Feigenbaum, 1990, that the relation one actually derived from the special relativity like this one. So as a function of a constant Q, a new constant to be introduced, where K is merely an additive factor that fixes a 0 point of energy. So therefore, K is the what you call calibration value for that E sub naught or the energy at rest to takes place. So there's somewhat in the field, in the plane, there should be one particular origin, and that is said to be the calibration value of K. However, of course, as mentioned, and is conventionally set to 0 and Q is also routinely set to 0. So, a set value of origin. However, unlike the conventions to set K to 0, setting Q is 0 involves a hypothesis concerning the nature of matter. So, therefore, Q is inherent to what particular matter we are talking about, as this paragraph suggests. So, the matter of conversion into another energy is an argument to be, an argument to be considered. Likewise, the same property interpretation of mass and energy and equivalence rests squarely on the assumption that Q is equal to 0. So meaning there should be a true value of Q. Mass and energy cannot be the same property if there exists matter that has mass, some of which cannot ever, under any condition, be converted into energy. Kumbaga, there is what we call a conservation happening on the mass into an energy. However, one could argue that although the same property interpretation makes the assumption, it is not the unjustified assumption. Currently, the physicists do not have any evidence that there exists matter for which Q is not equal to 0. So they need to identify and validate that Q is not equal to 0. Okay? Nevertheless, it seems important from a philosophical point of view to recognize that the same property interpretation depends not only on what one can derive from the postulates of so many concept of special relativity, but an evidence from outside this theory. So there should be a need to view some other factors. So that's why there is an interesting value that Q, no, of 0 value is an argumentable condition. So finally, the interpretation of this equation is sub naught equal to mc squared that hold the mass and energy are distinct properties of physical system need not, of course, assume that Q is different from 0. So therefore, there can be some similarities and differences when it comes to the application. But such interpretation can simply leave that the value of Q to be determined empirically. So therefore, there can be, assumptions to be removed or eliminated that is not participating, or there are no uh, factors at all that might influence the value of Q. For us, we have seen such interpretations argue for treating mass and energy as distinct properties and on different grounds. So, nevertheless, the Bondi-Spurgeon interpretation does seem to adopt implicitly the hypothesis concerning the nature of matter. Now, to have a picture of what we are discussing earlier. So according to the special relativity, the mass of an object approaching the speed of light increases. This equation is taken from the combination of Lorentz factor, Einstein's relativity, that relates to relativistic mass, no? And also any object that with a rest mass of m sub naught has an equivalent rest energy given by E sub naught is equal to m sub naught c squared. Essentially, energy and mass are equivalent and transmutable. So that's why this equation exists. And don't forget that the total energy is equal to the mass times the square of the speed of light times a particular factor of Lorentz condition gamma as a function of velocity. So that's it, and these are the references of my presentation for today. Okay. I hope you learned from this discussion for today. So this is all about principle of relativistic mass and energy. And then this can be followed by my discussion on some problems solved regarding to this problem to better execute and understand how do we deal with relativistic mass and energy as a principle. Okay? So thanks for viewing. Please subscribe to my YT channel and don't forget to hit the like and share button below. As a tradition, you have been neurorized and thanks for viewing. See you next time in our next video lecture, which is the solve problems or the problems that we want to understand and to be solved using the relativistic mass and energy based on a reference book. Okay, see you next time and have a nice day.